All right, welcome back, everyone. We have some talks on agent evaluation and benchmarks, and our first speaker is going to be Anastasios. If you want to come up with LM Arena. Welcome, Anastasios.
All right, everybody, thank you. Honored to be speaking here today. I was a student at Berkeley not too long ago. Actually, Arena started as a student project. It was just, I was a PhD student here. I was working with Mike, Jordan, and Jitendra Malik. And we kind of had this collaboration with Jan Stoica, who, as you guys know, is the first CEO of Databricks and also a professor here, that turned into the Arena. All of the model labs started competing on our platform, and now it's become a company which has grown sort of gangbusters from there. And so some of you might have seen it online. But here, I'm going to tell you guys a little bit about how we evaluate agents. Of course, this is the conference for agents, so it won't be any surprise to you. But we recently released our new Agent Arena about 7 weeks ago that has led to millions and millions of users online using agents on arena.ai and us being able to extract organic signals of utility to people for agentic tasks. So with that, a little bit about Arena. Arena is the evaluation company. The purpose of Arena is to say that static benchmarks and so on, they have a lot of flaws. You can overfit them, and then there's also often a distribution shift between what you can collect a data set for and what actually happens in production. Arena works a little bit differently. Our philosophy on evaluations is that there's only one judge that matters, and that's reality. Reality is actually the source of objective truth. It's our way of measuring the post-deployment impacts of models, and it can't be gamed because it's actually just in order to do well in reality, you needed to have like real people's jobs and then be able to complete them successfully. And so we measure intelligence in the real world. And I'll tell you a little bit about the way that we do that. Long story short, Arena has a consumer application, which is arena.ai, that you guys can go visit today. I'll tell you a little bit about it in a second, but we collect two types of data on Arena that we can turn into benchmarks. I've shown the two up here on this slide. The first type of data, which you might be familiar with Arena for, is pairwise preference data. Okay, so that's one prompt and then two responses, and then the user votes for the better response. Now, this is sort of like not on the talk track, but I'll tell you guys, there's something that I call the fundamental principle of Arena, which drives all of this. The fundamental principle of Arena is that the act of providing feedback should give value back to the user. And that's what allows us to collect millions and millions of data points like these, like without having to pay people, right? People are coming to the website and using it for free, and then in doing so, they're giving us valuable feedback that can turn into evaluations. And the way that we give value back to the user through the voting mechanism is that when they vote for the response that they like better, they continue with it in the chat. So anybody that doesn't want to screw up their model's context is incentivized to vote their true preference. And so this has led us to have quite a few high-quality votes on the platform. The second type of data, which you might be unfamiliar with Arena for collecting, is called trace mining data. So here, it's away from the battle mechanism, so it's one prompt, one response, and then there's these long multi-turn conversations happening over days and weeks on the platform that we can mine for signals. So here I put an example of a user that architected a RAG financial brain. You can read this text. Architected a RAG financial brain that ingests, cleans chunks and embeds finance articles, blah, 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 a full architecture flow chart and a passing 160 test suite. And this was all done in Persian. So it was an 84-turn conversation over many days in Persian with 600+ tool calls. It's just very, very rich data. And from this, we can mine things like task completion signals, users telling us explicitly through button clicks whether or not they got their job done or not, hallucination rates, steerability, these are all done through automated pipelines, error rates, user frustration, user praise, user negativity, and then report these back to you guys, which is what we do in our leaderboards. So I'm going to try to do this. So just to give you a sense of scale, by visits, if you look at startups founded since 2020, Arena is actually just top 10 in terms of raw users. A lot of people don't know this. We're bigger than XAI. We're bigger than Hugging Face. We're bigger than Manus. We're bigger than GenSpark. There's 35 million monthly visitors. It's a freaking massive flywheel of all these users. And 28% of them, by the way, are doing software. And so what this means is that we have the equivalent of like 1,000 SWE benches every week of like real world coding data that we can use for evaluation on this platform through our sort of community evaluation model. It's really amazing. This is a little bit more on the data collection the sort of like user base that feeds this data flywheel. You can see there's 28% software. It's like 17% sciences, 12% finance, 10% math, 6% legal, 6% medicine, all using these sort of agentic cross-provider workflows on Arena. I'm going to show you guys a demo of the agent Arena here. So this is what you might not have seen. This might be new to you, but you can go use it on arena.ai today. And so what you'll see is here the user says download Google's Q126 earnings call transcript and create a PowerPoint with key results. And what happens is that we spawn off a computer. The agent can use a computer, and then it'll go search the internet. Oh, let me find the earnings call report. I'm going to download it into my workspace. And then I'm going to use Bash to create a PowerPoint. The user can view that. They can scroll through it, blah, blah, blah. Platform's actually gotten much better since we took this video. Then they said, let's keep working with it, and let's turn that into a website and make it more Google branded. And so they did that, and now the model is again going to use Bash in order to create a website. It makes the earnings call website, and then you can see it here. And then at the end of this whole experience, if they're happy, well, again, they're not, they're incentivized to do this only insofar as they're getting better responses. They can then click at the bottom there, yes, my task was successful. I'm going to move on to my next one. And this is the type of feedback that we can collect. Every message the user sends, that's an opportunity for feedback. If they say, and many of us in this room have done this, we've gone to a model and said, screw you, I hate that response, that sucked. That is a great piece of feedback. It's very high intent. We all know what we mean when we say F you. And then sometimes you'll say good job. Now, a little bit of an aside here, again, like a tangent to the main thread. You can't believe how much money everyone in this room is spending just saying thank you to Claude, okay? Because what happens is that you'll have like a 20-turn conversation, and then somebody will be like, thank you, good job, enter, and that costs you $10 because all that context was in that. So be careful how you spend money, okay? Okay, now what do we actually do with all this data? How do we report these leaderboards? Now, again, some of you who have known the historical Arena might be familiar with the Bradley-Terry model or the ELO mechanism that we sort of introduced to this space. Of course, it's an old statistical methodology. And so this is another example, now that we don't have pairwise preference battles to do ELOs, of how we have brought some old tried and true statistics ideas into the foray of AI evaluation. And here we're doing causal inference. So the idea is very simple. In these agentic threads that you see, like in the previous video that you saw, you didn't see the model. And so what that allowed us to do as Arena is intervene on the system by randomizing the model, which allows us to then do causal inference. Okay, and by causal inference, what I mean is to say that you can think about, let's say, the orchestrator in the agent or the tools of the agent as a treatment, and then try to measure the treatment effect of what would happen if you used one orchestrator versus another. What happens if I use Fable as my orchestrator model as opposed to using the baseline model, which might be a randomized average of the rest of them? And so that's what our leaderboards actually show. If you go to arena.ai/leaderboard, the default leaderboard that you'll see will be the agent leaderboard, and it will be a treatment effect-based leaderboard that runs a basically large multi-factor A/B test experiment on all the subcomponents of the agent. And then what we do is we compile that leaderboard out of a bunch of different signals. One of the signals is that task completion. Yes, no, my task was done or not, that you saw on the previous video. But we also have all these other signals like praise versus complaint, which is the fraction of positive versus negative feedback that users are giving to the agent. We also have hallucination rates. We're stripping every factual claim and then using a bunch of search models to go look along the internet to try to see if we can verify that claim or verify that it was incorrect. Steerability, which is a user will say something, the model will respond, and then is the user kind of struggling to do the same thing over and over again, or did the model correctly land the fix after they initially complained? Bash recovery, is the model able to recover from errors that it makes in Bash? Does it make errors in the first place? All of these are very rich signals that you can mine from organic data. Would be surprising because, of course, if you go look at any benchmark, models are not making errors at all because they've all overfit to them. But here in reality, you go to somebody's actual real use case like many of us have, and it's a very different story. So you can do that, and then you can break these causal inference, these treatment effects out in terms of things like cost per task or latency. You get very rich analysis of performance. So you should take a look at that. Yeah, so this is a little bit more of an explanation. Every week we're getting like millions of agentic traces, implicit signals, explicit signals, environment signals. We're turning these into like signal by signal leaderboards. So this is the causal effect leaderboard as of a few weeks ago for confirmed successes, which is that explicit button click. And you can see there's confidence intervals on these that are determined through limit theorems in a standard way. And it's all a treatment effect that's based on that gray line in the center. And then what we do is then we aggregate these signals. You know, we have a bunch of them. We have like 25 now, actually, into a leaderboard via a weighted average, which we can do. That's another benefit of the causal methodology, by the way, is that it allows you to combine many, many signals into one coherent leaderboard. And that's what we do. Allowing for these, like, you know, extracting many signals from deep workflows and then combining them into a useful summary signal of the model's performance. This is the leaderboard as of, you know, a little while ago, a few weeks ago, and it's obviously changed a bunch since then. Fable, I think, remains the top on the agent arena, but Kimi has given it a run for its money. So yeah, that's a little bit. That's, you know, the majority of the presentation here. I'm not sure if we have time for questions, you know, or if we're doing questions from a technical perspective. But if you guys are ever interested in working in this kind of stuff, the intersection between deep mathematical statistics, causal inference, you know, estimation theory, and AI evaluation, trying to push the frontier of how we measure these models' performance, you should absolutely contact us. You know, you can find me on X or Twitter or whatever you call it, or email our team, hiring@arena.ai, anastasios@arena.ai. Would love to talk more with you. So thanks so much.
Next up, we have, let's see, Mikal with IBM Research.
Good afternoon, everyone. Are you ready for general agents? Let's test it. So this talk is based on 3 publications from iClear, ICML, and hopefully new RIPs very soon. Okay, so if you look on Richard Sutton's bitter lesson, then we basically means that generality ultimately wins over domain-specific approaches. Looking back on machine learning, AI, and even if we look not that back on language models, so we all started with domain-specific models doing tasks like summarization, extraction, and so on and so forth. And eventually we all moved to big models that can actually are capable of doing all different type of tasks. If you're looking on agents today, we mainly see what we call domain-specific agents, which are basically agents doing finance, customer care, or any specific domain. And we, and also some other colleagues, I mean, just from learning from the past, saying that the future will go to what we call general agents. So what are agents and how we evaluate them? So I think I've heard it many times during this conference, but basically agents are a complex, they are the LLM that is there, along with the harness, the memory, reasoning, search, and so on and so forth. The agent is interacting with an environment via actions and observation through some protocol. And if we want to evaluate the agent, then we have usually a benchmark, and we prompt the agent with a task, and we collect the outcome from the environment and calculate the metric. So we define domain agent as domain that the agent, the knowledge of the domain is encoded within the agent. So basically, once the domain, the knowledge is encoded, the agent can start working with the environment. When we say general agent, you no longer see the domain-specific knowledge within the agent, and we assume everything is on the environment side. And we basically looking on the adaptability of the agent to explore and work with new tasks. And eventually what we are pushing is that if we have this model, then the general agent can work with different type of environments without the need to re-engineer for each one of them. So when we talk on general agents, it's no longer deep performance in a single task, but we want to understand how it works on many different environments and tasks. So the main promise here is that one general agent, you can use it for many use cases. You no longer need to have, I don't know, like 100 different domain-specific agents. There is a centralized approach, the effort, so we improve it, and all the use cases benefit from the improvement of the memory of the search and so on. And also, like we have now in LLM, if we start with the starting point is a general agent, we can still customize it, but the starting point is much better. It's a better and robust agent that we should do. Saying that, I know that there are other views that domain-specific agents are important because we have more control. They are more efficient and also more predictable. Other issues could be around the risk. I mean, we give the general agent more autonomous, which can lead to unforeseen risk. Some also claim that the model should be general and not the agent. And actually, I encourage you to read the paper. It was a position in a paper in ICML, and you can understand both views in details. So let's assume that I convinced you that general agents are the future. In order to say that an agent is general, we have to make sure that it is indeed working on different environment and tasks. And how we do it, we need to evaluate. However, here is the trick. It's not a trivial because there are issues of standardization, mainly on the agent interface, environment interface, and the researcher interface. And here, I think, contrast to what we saw in the LM arena, we are talking about benchmarks that are open sourced by, I know, many students and many other efforts that we are using them. So if you look on issues, so we see for the agent interface, each benchmark, they expect the agent to work differently. From each agent, expect the environment to provide different information, and also the researchers, each one implement its own code for the agent benchmark combination. And this is not scaling. I mean, if we want to try many agents on many benchmark, it's just not scale. And if we look on what exists today, and again, I'm not going into details, you can find everything on the papers. Looking on all the frameworks that exist, you will not see even one that support multi-protocol benchmark, multi-protocol agent, agent plug and play, and the generality. So looking on very different tasks on very different tasks. And this is actually where we are stepping in. And we develop a framework for agent evaluation. It's called Agentic. And here you can, bring in any general agent that you have, any benchmark, and it supports all the type of integration. And how we do it, again, I'm not going into details, but the main idea is that we introduce a new mediation layer that we call the unified protocol. And so still the agent using the protocol that it comes with, and similar the benchmark, it uses the protocol that it was developed with. And what we are doing kind of a transformation between those two. So we are not changing anything in the benchmark, so they work as they intended. And similarly, we are not touching the agents. We're just doing the mediation layer. And this is based on the commonality that we saw across benchmark and agent, with basically the three primitives of task, context, and actions. So given this, we publish what we call the Open Agent Leaderboard. And this approach allows us to take any agent harness with any model and any benchmark and do this Cartesian product. So what we see. So basically, as you see, we have the agent column followed by a model, and then all the tasks, and we calculate, of course, the average success. But in addition, we also calculate the cost, which are, of course, important. And then, again, we can look on the Pareto frontier, and based on what you are after, you can select the specific configuration that fits you the most. So it can be very expensive if you want accurate work, or if you can have some less accurate, you can go for the cheaper models. Okay, what other insights that we already get from the results? So I think the first insight is that general agent, they adapt without any needs to do something. And we see that on average, again, most of them can do all the tasks. I didn't, but they can do all the tasks that we introduced to them. Currently, the model matters the most. I mean, the quality of the results is mainly driven by the model, but we see also some effect of the agent harness. Another point is that, and I focus here, is that actually when we compare the quality of the general agent versus domain-specific agent, and here what you see is for each one of the tasks, we went to the leaderboard and took the top domain-specific agent. We then compare it to the top general agent, the results that we got on our evaluation. This is the blue, the top line. You see that they are quite competitive. Without the need, we didn't touch the agents, so no need to do this re-engineering and engineering, and it still works quite well. One also not surprising, but I think important point is that while having similar scores, we see that agents behave differently. So we see that some agents, they fall very cheap and fast, while others spend you a lot of money. At the end, both are false. But it's important to understand those effects. And one more point I want to put is on the open weights model. So in general, we can say that they are not general reliable. And to give you some information, so first, on average, they are behind the closed model. You can see it here. We have Kimi and DeepSeek. And then we see that in some tasks that probably they were not trained on, they really failed. I mean, they sink. So this on the left is what is known as upward application, different task of application. And you see the quality of Kimi and DeepSeek, and this is average on all different harness. So we have 5 agent harness, and on average, they could not perform well on each of these combination on this task. So they are just not doing well on some of the tasks. I think another interesting point is that the open weight model are more sensitive to the agent harness. And what we see here on the right. On the right, we see, for example, for Kimi, we took the Kimi with the best harness versus Kimi with the worst harness, and we see there is a 18% difference. And I think this is very important and has a lot of implications, which basically means that you cannot just change the harness and assume that you will get the same quality. For the open weights for the closed model, it's quite, it's more safe, but when you move to the open weights model, you have to be much more careful, and you need to do the evaluation if you want to change the harness. And on the other side, you see that when we looked on OpenAI agent, and while for Claude and Gemini, it really lifted the results, When we combine it with the open weights model, they just, zero, they just crashed. So it's not that you can fit any model with any harness. You have to be very careful about it. Okay, I just mentioned that I've heard that they are cheap. I mean, in one of the other talks. So it's not always the truth. So if you look on the cost quality, they are not cheap, they are competitive. So again, we tend to think that they are cheap, but it's not always the case when you look on numbers. Finally, just to let you know, when we run Agentic, we collect all the traces in OTL format. It is open source. It's on a Hugging Face. There are more than 10K traces that you can collect and understand how the agent, the whole full traces. Okay, what is next? So actually, we are now coming with the Agentic V2. It's a little bit different approach, that something that we learned from V1. It's based on the primitives of Kubernetes and Dockers. In addition, we are working on evaluation of agentic inference platform and the new topic of AI native system evaluation. So if you are in either one of these topics, just approach me. Thank you.
Thank you, Mikhail. Next up, we have Priya with Scale AI.
All right. Good afternoon, everyone. I'm Priya Ponnapalli. I'm SVP of Engineering at Scale AI. Scale's mission is to build reliable AI systems for some of the world's most important decisions. And this is a hard problem, right? You have technology that is inherently stochastic, and you are trying to deliver deterministic business outcomes using this. So Scale's approach to solving this is an eval's first one. Here's where our approach comes from. So 90% of frontier labs use Scale's data engine, and we have been building AI applications for governments, including the US Department of Defense and the Defense Innovation Unit, as well as for many enterprises in regulated industries such as healthcare, finance, and telco. And unlike consumer and prosumer agents, which you are using for day-to-day productivity tasks, reliability is really key in these enterprise agents and these regulated industries. For example, we are working with the Mayo Clinic on bringing agents to improve patient care. And here, the goal is literally saving lives. So there's no room for error, and these agents have to be extremely rigorous, robust, and well-tested. This is an area where mostly write just isn't good enough, right? There was an MIT study that was cited in this morning's talk about how 95% of AI pilots do not end up going to production. In an enterprise setting, if your agent is wrong even 5% of the time, that's a liability, right? This could be like a wrong number on a customer invoice. It could be a misstatement in a compliance filing, a bad write to a production database on which thousands of downstream systems depend on, and it's just not acceptable. So at Scale, we have a framework for building reliable agents, and we hold every production agent to 8 engineering gates. These span everything from ensuring data privacy, ensuring the right access control frameworks with the right auth and auth in place. But the area I'm going to dive in today in this talk is on rigorous evals. So unlike a model benchmarking exercise, there's a shift in how you evaluate enterprise agents, which is really a system reliability capability, right? Yeah. An agent is unfolding over time. It's interacting in a real environment. you're not just evaluating a model and its output text anymore, right? You have to evaluate an end-to-end system. This includes the model, the prompts, the tools, the orchestration, and the environment, which in an enterprise setting could include production APIs, knowledge bases, various files, workflows, business workflows that are present at that enterprise. And an important and useful distinction is understanding which components can be tuned and which ones are given. And good eval design keeps these separate. So here's what's at the core of our evaluation framework. We have a layered evaluation framework where we keep the business alignment, the black box evaluation, and debuggability separate, but still causally linked. So at L0, we've got the business outcomes. These are our North Star KPIs. This is the value that the agent actually drives. This could be, the resolution rate, cost per ticket, analyst time saved. At the L1 level is the task success. Here we treat the agent as a black box and ask if it successfully completed the task. Examples of this are, was the refund issued to the correct amount? Is the case record in the correct final state? So this is almost the operational center of the agent evaluation and what we iterate on, try different approaches, and look at changes to improve the score. Going a level deeper is the level 2 component evals. This is where we're opening up the black box and looking at the subtasks. So you have things like extracting relevant facts, choosing the right fields, producing the right record changes. And finally, level 3 are the diagnostics. This is what is needed for debugging and optimization. This is the why behind why the level 2 and level 1 metrics may be failing. And all of these form a chain. So a common failure mode is teams might end up spending more time optimizing on the level 3 and level 2 diagnostics and components, while not ensuring that level 1 is also improving. So now let's take a look at this framework in action in some real-world examples. So Scale is helping a top oil company with designing oil wells better. And this includes the casing design. So casing is the steel pipe that goes around the well. And the process for designing these casings is often a multi-week hop where an engineer is running hundreds of simulations. They're referring many standards that are buried in PDFs and libraries. So our approach to designing this agent has two key parts. One is a deterministic core, where the engineer is still in charge running all these simulations using trusted physics-based simulators. These results are checked deterministically against company standards, and the engineer makes the final call on reviewing and approving safely designed wells. The second is a casing design agent, which is following along with the engineer. It's extracting all the right context from hundreds of simulations. These are all grounded in the agent's interaction. The engineers are allowed to ask questions, which are all answered by the agent with clause-level citations. And the agent finally designs the well's design doc. This is also known as the basis of design. And it's worth calling out that the agent never computes any number or drives any workflow. So by design, numerical fidelity is 100%. So the eval exercise boils down to how well does the casing agent answer the engineer's questions and generate complete and correct BODs. So to evaluate how our agent is doing, we apply the same 4-layered eval framework, where L0 is the number of annual BODs that have been signed off by the SMEs. L1 is, does the agent design and answer complete, correct, and review-ready docs? L2 is focused on retrieval and context management, and L3 is around terminology, grounding, fidelity, and recall. So we build the evals with our SMEs We calibrate the graders. SMEs are often bottlenecked on time. So we synthetically expand their SME templates and then have them validate the additional data. We hill climbed on L1 correctness. We were able to get the terminology precision from 83 to 100% and the claims precision from 68 to 90%. This got the confidence of the customers' engineers, the Wells Designs engineers. And we're now in a limited production rollout where we're going to collect additional production traces, score them, evolve the eval sets, which needs to be a living asset, and improve the agent from here. So worth noting that evals are living assets, in my opinion. They are the most durable asset, right? You can always swap out the model, various aspects of how the agent is designed, and test against this eval suite. And this is truly like the IP moat of where our customers invest in and what helps them keep up and like ride on top of the wave of foundation model improvements. Another example, this is our work with a top 4 professional services and accounting firm. This is where we built a financial due diligence agent, which helps analysts get to the same human validated insights, which was taking them 4 to 6 weeks down to 2 days. So again, it's the same eval framework. We define L0 as the total time to human validated insights. We've got all the layers. We've built the evals. We've improved on the L1, hill climbed and improved on the L1 correctness. This is also going to production rollout where we learn from every run. And oftentimes having sufficient eval data is one of the biggest bottlenecks. So these limited production rollouts are a great opportunity to collect additional data and like evolve your eval suite. So for every agent built at scale, we hold an eval design review. We have a forward deployed engineering team that partners with all our enterprises as well as government agencies in building them. This is the performance maturity matrix we used as an eval scorecard for every agent, and we don't ship until the scorecard is all green. So wrapping up with some key principles, I'll call out a few. You are evaluating systems, not just models. Use hybrid graders, so deterministic wherever possible, model-based where necessary, and human review for calibrations and high-stakes use cases. And treat evals as living assets, grow them over time. This is your asset. And evals first is how mostly right becomes production ready. So if you are in the space, I would love to compare notes. My email is up there. Thank you all.
All right, thank you. Next up, we have Srijit.
All right, good afternoon, everyone. My name is Srijit Rajman, and until recently, I headed AI research at Redis, and today I wanted to talk a little bit about the agents that a diagnostic and remediation agent that we built for diagnosing issues with the Redis query engine. So we primarily built this as an agent to help our customer support agents with many of our customer queries. So Redis does provide a pretty rich suite of tools and pretty extensive documentation for these issues. What we really notice is that at the end of the day, many of these complex queries get escalated all the way to the development team, which is obviously not conducive. So we built this to see if we can unblock many of them and reduce the time to solution for many of our customers. So what makes this challenging in particular is that unlike something like SQL, the parametric knowledge within an LLM is pretty limited, and we see that it gets it wrong quite often. So, and some of these queries are pretty context dependent anyway, where the agent must know what's actually missing from my query. So we had to build this spec-driven agent with skills and tools that goes through this clarify, diagnose, confirm loop in order to make this more reliable. So some of the things that we learned in doing this is that evaluating the final result is often pretty insufficient. How you get there or the trajectories matter quite a lot. And obviously, correctness is pretty important, but so is consistency. I like to say that the only thing worse than a system that doesn't work is something that just works occasionally. So this is something we really want to avoid. And lastly, inefficient trajectories are obviously expensive. One of the things that we learned the hard way is that these are also pretty error-prone downstream as well because of the length or context exhaustion as well. Obviously, using a more frontier model or more capable model will resolve some of these issues. What actually moved the needle for us was actually restructuring some of this knowledge and how agents access information. So essentially, we wanted to make sure that we provide sufficient information that it knows how to identify and access information and when to use it. So a couple of things that I actually want to call out here is these are some of the failure modes that we saw when we're building these agents, and I classify into 4 buckets roughly. The first, the correctness, completeness, and usefulness relates to the final results, and efficiency relates to the trajectory. Correctness is pretty obvious. Obviously, if your result is wrong, that's a problem. It can stem from a number of reasons, such as paths being wrong, it reads a metric incorrectly, and so on. So these are just hallucinations. Completeness, this is when it diagnoses only part of the issue and leaves the others unresolved, which is a pretty commonly occurring issue that we've seen. So usefulness actually falls into 2 buckets. The first one is when it actually gives you plenty of information, actually too much information, or very generic information to the point that it's really not actionable for the user. It is just overwhelmed with information. And the second one that was actually pretty interesting for us is when it provides information or advice that violates semantic intent. For example, telling a user who asks why my query is slow to reduce the number of search terms is technically correct, but it doesn't actually serve the purpose at all. The last one has to do with efficiency when the agent actually has repeated reads, backtracking, or does dead-end searches, thereby resulting in wasted tokens. But also, as I mentioned earlier, one of the things we noticed is that this also affected accuracy negatively as well. And most of these things can only be resolved by looking at the trajectory. They don't show up in the final result below. So we addressed this in 2 ways, or 2 dimensions. The first one was, can we actually take a look at the tool architecture, and what can we do there? So there are 2 things that we actually did here was primarily, can we split up the tools into 2 categories of setup tools and discretionary tools? So setup tools are always called at startup, as opposed to discretionary tools, as the name indicates, are called by the model based on the problem that you're solving. So a way to think about it is if you're starting on a new role, you might go through an onboarding process where they teach you what's happening there, who's doing what, who to talk to, and so on. So we can think of it that way, where the setup tools provide enough context for an agent so it knows how to proceed correctly and use the discretionary tools correctly, and it knows when to use it correctly. The second one was actually how we organize our knowledge base. Obviously, you can use the raw documents by themselves, but we saw better performance when we reorganized this into what we called a diagnostic playbook. This is nothing but a router plus a set of handbooks. And you can think of the router as, I've shown a small structure or snippet here, is you have symptoms, and you have a problem type associated with that symptom, and route to a handbook or a set of handbooks. So users don't come to you with saying, I have a certain symptom, they have concerns. It's the agent's job to actually map the concern to a symptom or a set of symptoms. Our job is to make it easy for the agent to do that, so that's what this serves. And in order to understand the effect of these interventions, we studied these separately. So we learned in doing this, so we tested over a number of data sets, is we measured the end-to-end latency, but we also looked at the number of tool calls and the quality of the results. So the first one was a baseline setup, which was automatically generated set of tools. We noticed that it doesn't exactly perform as expected. It was slow, and the quality of results were actually pretty debatable. The last 2 I call minimal and full. They were actually generated by domain knowledge. They were informed by our domain knowledge of how Redis query engine works. So the difference between minimal and full is that full is a superset of all the tools you might find in minimal. So a way to think about it is if you have a tool such as get shard info, and you want to find out what the slowest shard is, you might have to call that and then perform some processing on top of it, as opposed to full, which might have get shard info and get slowest shard. So you just simply have to call it. Interestingly enough, that one did not perform any better. In fact, it was slower, and the quality was just marginally worse. So this sort of goes to show that tool overload is very much a real thing. And more importantly, what I'd call tool orthogonality or separability is pretty important. So at any point, if an agent is unable to determine if I should call B or C, it's problematic. So with setup tools, what we found out is that this is simply just minimal, except what we do is we moved a subset of those tools into the startup time. So what happens there is now it only has to make a selection between a smaller set of tools as it solves a problem. And here, with setup tools and minimal, they perform pretty similarly till we took a closer look or drill down into the trajectories themselves. So what's interesting here is that with minimum, without setup tools, the trajectory is actually way more inconsistent. You have a lot more unique number of sequences. Obviously, not every unique sequence is an issue, but some of them can be problematic. The takeaway here is that reducing the number of variants, reducing the decision-making that an LLM has to make at any point reduces variance and also improves the consistency. And we were able to do this by providing setup tools which forced an onboarding context. The second dimension was actually organizing information to playbooks. So how did that impact our results? So we organized this into two sets of buckets roughly, which is the answer quality and the trajectory quality. So answer grounding and specificity relates to the final results, whereas first pass success and dead end rates relate to the trajectory themselves. Across the board, we see improvement in performance when we're actually using playbooks as opposed to reading the raw guides. We also saw a 43% reduction in the total number of tokens and a 48% reduction in the total error rate. If you look at the last row there, what's interesting is that it also enforces instruction following a little better as well. The call out here is that reducing making it easier for it to actually access the information not only reduce costs, but also reduce forgetfulness and thereby improved reliability. So obviously not everything is working as expected. There are things to be improved there. One of the things this is actually a prime candidate for are things like recursive self-improvement, which has been a pretty common theme at the summit here. So we'll probably have to look into something like that to improve performance even further. But we do see a reduction in many of the common failure modes. And lastly, to wrap up, if I can leave you guys with any takeaways here, there are two things I want to call out is measure the trajectory, not just the final answer, because many of the issues that we saw did not show up in the final result. We had to inspect the trajectories themselves. And if it is possible, structure the knowledge in a way that it's easy for an agent to identify and access, and take a look at your tooling to see what is mandatory baseline context versus what's discretionary or exploratory context. And the final thing I'll add is, if you can get to correctness, completeness, and usefulness of your result, and efficient trajectories, you're more likely to have production reliable agents. Thank you.
All right, thank you, Srijit. Next up, we have Sergey Gukov with Caltech. And this is our last section. This is going to be math, AI for math.
All right, I'm Sergey. Good afternoon. This session in some sense is a natural continuation of benchmarks and evals because mathematics is a natural way to benchmark AI systems. So AI has been progressing through different levels of complexity that I outlined here, different levels of difficulty of math problems, going from elementary school to middle school, then to high school, graduating into college. That's actually where AI systems roughly are right now at the level of consistent performance. Keyword here is consistent so that they can solve problems really reliably with high fidelity. And then as a professional mathematician, to me, this hierarchy goes on and on. In fact, there are graduate level problems which we give on various hard exams. Then there are graduate level problems that we assign to students. And if they solve it, they actually earn PhD thesis. And then the hierarchy continues into professional math research. There are several levels there, including problems which we as research mathematicians have no idea how to solve. There is gradation there as well, which includes perhaps Millennium Prize problems at its highest level. And this talk is about a question whether AI systems can reliably reach that highest level of performance. In other words, you can think about this talk as, can we get artificial superintelligence? It hasn't come yet, but question is how far and what are the bottlenecks? So it's easy to benchmark. As I said, this talk is in a way benchmarking talk because there are lots and lots of math problems. For example, website over there lists for you about 100 unsolved hard math problems, which do include all the Millennium Prize problems, but there are plenty of others. Among these problems, there is a very simple one, which I myself didn't know about, but surprisingly, it's easy to state, but hard math problems that belongs to that list. It's like, what is the longest snake you can fit in a hypercube? So imagine a cube of size 2 by 2 by 2 and some number of times up to dimension. And so in other words, each side is length 2. So question is, what is the longest snake you can fit in such cube in d dimensions? So when I heard about this problem about half a year ago, I thought that for large D, we can probably make progress with AI, because for small values of D, mathematicians and computer scientists probably have figured it out. So it turns out that the system we built managed to beat the record, which for a long time has been standing even in dimension 9. And this is an easy-to-state problem, but it has connections to cryptography, quantum computation, and other domains. So what I like about math and benchmarking on math is that you can try on this problem, for example, with any system you want. So for example, you can throw Fable at it or AlphaEvolve and see how it does. Of course, we have tried and nothing happens. I mean, it just doesn't solve it. So what are the bottlenecks? Let's look at another problem. So this is another one we tried recently, and this problem came from a professor here in Berkeley, David Eisenbud, who suggested this problem as a really hard problem on commutative algebra. And we managed to solve it, and I'll tell you a little bit about the journey by the end of the talk, how it went. But here the problem is to look for some esoteric concepts in commutative algebra, monomial ideals with two properties. And it's easy to find monomial ideals with one of the two properties individually, but once you combine them, you're looking for a needle in a haystack. So that's where probability drops to 0 in this distribution plot. So we struggled a little bit and designed several, in fact, many systems through all kinds of AI systems at it. It was very clear that it has hierarchical structure, this problem, that there are two steps and they should be outsourced to two different individual components of AI system. But then even once you know that you want to approach it with some version of other multi-agent system or HRL, it still requires a lot of iteration to find the right one which works. So here we had to design architecture which is ideally suited for this problem and lots of other things. So the third problem I'm going to give in this talk as an example is from yet another area of mathematics. This is from group theory. The problem is called Andrews-Curry's conjecture, and that's another problem that's been open for 60 years. So here, the problem is very much like Rubik's Cube. In fact, many problems in group theory are kind of like Rubik's Cube. So you're given some state, and the goal of the agent is to find a path to the goal state. Goal state for the Rubik's Cube is where all faces are colored in the same color. So this is kind of a glorified version of that. Except that in this case, the search graph is not explicitly presented, and the problem itself is asking, can any state reach the goal state? So that would be the CS formulation of this problem. So again, we managed to make progress on it, and all of our papers are published in ICML, ICLR, and Europe. Even though they make progress on math, we have to design AI systems with lots of interesting bells and whistles and insights. For example, in this case, one of the insights was the data distribution on the problem, that in Rubik's Cube, it's easy to scramble and generate data on which you would be training it. But here in this problem, what happens is that this distribution of the data is very bimodal. In other words, scrambling and just random search and so on gives you very primitive data which is in the vicinity of the goal state. But there are some states here which are super exponentially far from the goal state. And the question is, how do you train RL to reach those, kind of the other hump in this data distribution? So these are kind of problems that we work on. And now I can do a proper introduction. So I lead a lab at Caltech, which is laser focused on solving math problems, but really what we're really focused on is building AI systems, AI tools for long horizon and sparse reward problems. Because if you ask what's in common in the problems I just mentioned, and that's actually going to be the feature of any really hard mathematical problem, is that your system will have to reason for many, many steps, and even if you have very high fidelity, it can fail over 100 steps, but 100,000 and 100 billion steps, that's actually what we need for these problems. That's where you need not just 30% improvement, but really many, many X% improvement. So these two issues, long horizons and sparse rewards, each are challenging, but when combined, they just become notorious bottleneck for all these math problems. So it's good to look at other domains where either long horizon or sparse reward tasks occur, and there are quite a few. So it starts actually with Atari games, and I'll come back if I have time to games and AI for games. Of course, coding, robotics, autonomous transportation, all these tasks require either long horizon or sparse reward or both combined. There are some things that we know how to do, so various exploration, curiosity modules. They help to generate, turn a sparse reward problem into a more dense signal that we can explore gradually and generate sub-goals and subtasks to solve the main problem. More recently, learning world models, of course, is very helpful, but again, it gives a few X or 10X improvement, not billions of X. So that's what we really need. There are all kinds of bells and whistles, such as harnesses, that everybody and us are trying to use in various ways. But again, so far, none of the Millennium Prize problems has been solved. So the problem is still open. And there are quite a few challenges out there where we're debating whether LLMs is the right underlying framework. For example, can they reason, or are they just good at retrieval? So that kind of generalization question is one of the vexing questions here. Another is, I already alluded to it, is a really integral part, which makes things more robust, helps to improve performance either in post-training, alignment in various stages, but is it really enough? We don't know yet. So again, for this superhuman reasoning, that's going to be the question. If you look at SWE bench, then yes, coding agents are pretty good now. Performance usually ranges in 70, 80 percentile. But if you ask what are the bottlenecks in this remaining 20%, it's exactly this long horizon tasks, where if agent has to fix some bugs in the code spread over several Git repos, find different files, then it gets lost. In particular, because over this long horizon, it knows that there are several components, but detecting where exactly the bug is or what exactly has failed, that becomes a challenge. I mentioned that in terms of computer games, that's also a good comparison. So going back to DeepMind's DQN algorithm, which was introduced in 2013, it failed miserably on this game called Montezuma Revenge, which then became an obsession for AI or reinforcement learning community, trying to design the right algorithm which would actually do well on this game. And this became almost like a decade-long journey. So many teams tried, and many teams failed, until finally, by 2018 or 2019, we got some good signal, and now, of course, the problem solved. I want to point out that this period of exploration did include 2015 to 2018, when we had AlphaGo, AlphaZero, and MuZero, and none of those models actually performed well on this particular game because it was a good example of a sparse reward problem. So this is a good illustration of how it looks like to design AI system for math. You also try lots of different things, and pretty much all of them fail, especially if your problem is really hard, this long horizon sparse reward problem. So our cycle in our lab is very much the same research cycle as in any other AI lab. We design AI, we deploy it, we look at the W and B curves, we see what the signal is, most importantly, why it failed. So we try to analyze why it failed, and then we try to implement it in a new cycle, and so on and so forth. So this, in principle, can be fully automated. And I want to point out that currently we can't, for example, we can't do it with AlphaEvolve or other tools, simply because this version of algorithm development, algorithm design, discovery, is by itself a sparse reward problem. So unlike coding, where agents are pretty good, current agents are not so good at discovering really new algorithms way outside of the box. And bottlenecks typically have to do with evaluation, because your system is going to be just as good as evaluator. So in practice, what happens is that your evaluator sets up certain guardrails, criteria, conditions, and the agent quickly learns to hack it, simply because the original problem that you're trying to pose is just way too hard. And it's much easier to do hacking into one or the other type of behaviors. For instance, going back to OpenAI, this Coast Runner bot, which learned just to zoom over, collect some mediocre rewards instead of finishing the race. That happens in math problems as well. DeepMind had this Lego stacking challenge, where the robotic arm quickly learned that it's easier to trick the camera just to flipping the Lego blocks upside down so that the height appears to increase a little bit, and collect rewards in that way. And there is also, of course, reward tempering. For example, the Palisade research example, which is the last illustration with chess, where AI system managed to learn how to remove the opponent's engine completely in order to win the game. So this happens in all of the math problems, especially hard ones. Once you try to throw AI at it and you encounter same type of challenges. So the title of my talk is The Future of Math AI and Sparse Reward and Long Horizon Tasks. I'm actually very excited that we are at this point where for really hard math problems, to solve them not one by one, like I showed you in the beginning, but in mass production. So we can actually have super intelligence that can reliably solve pretty much any problem that I cannot solve as a working mathematician. So for this, we need to unlock this sparse reward and long horizon capabilities. There are many open questions. We're in a very good point right now, very sweet spot, where a lot of work has been done, but we're definitely far from solving this in the future. Just like in the past years, everybody would say that data is all the key, basically. You need clean data. Data is everything, right? So now, as we're exhausting data and entering the new era, I would say that for this new generation of AI systems, various tools and harnesses is going to be the new action space. And what replaces data stack is now reward stack. So setting right systems, like channeling the agent to go in the right direction, is exactly what we need for this long horizon task for sub-goal decomposition, which is reliable and so on. Of course, there are many other engineering challenges, such as it would be good to have this multiple agents work in teams for days and months, and that requires different AI agents to talk to each other, very much like we have with internet protocols in early days of World Wide Web and so on. And finally, I want to conclude with, I'm optimistic, I'm excited, otherwise I wouldn't be standing here and talking to you about it. So a week ago at International Congress of Mathematicians, 4 Fields Medals were awarded. So International Congress happens once every 4 years, kind of like World Cup, Soccer Cup. So I hope that 4 years from now, we'll see Fields Medal awarded to AI plus human. Thank you.
All right, thank you, Sergey. Next up, we have Lizzie with OpenAI.
Yeah, so hello everyone. So today I'll be talking about more like yesterday's news on unit distance conjecture and discovery. So the slide was made a couple of weeks ago, but as all you know, we have released 10 more new proofs on many major open problems in mathematics, but still good to revisit this discovery before. So the unit distance problem is a very simple to state problem, which asks, does every set of n distinct points in Euclidean two-dimensional space contains at most roughly linear many pairs which are distance 1 apart. So you are imagining putting n points on a plane, and you want to see how many points can have distance roughly 1. And this was proposed by Paul Erdős back in 1946. And it's one of the central questions in discrete geometry. So roughly 2 months ago, actually more than 2 months ago, we announced that an OpenAI model has disproved its conjecture, showing that you actually can have a construction with more than linear number of pairs. So maybe let's say a little bit more about the discovery. So this is achieved by a general reasoning model, which is not trained specifically for math. It's completely general. It's basically a version of ChatGPT. And it's discovered during a site evaluation of the model on some very hard math problems. Because nowadays it's very hard to benchmark a model against math problems since most of benchmark is kind of saturated. So you have to find some hard problem to test the ability. And essentially, that's no harness. You just give a model one prompt, and then just keep thinking about things, and maybe use some tools, and then it arrives at the final answer. And the model has access to the web and the terminal, so it can like search for what has been done before. Maybe let's say a little bit on the original construction by Paul Erdős. So the idea is that his original construction is just an m by m grid with a carefully chosen scaling. So you want to put many points on a plane, so you put them in a grid. And you scale that so that many of them has distance 1 apart. And the new construction, it's more complicated. It's a grid over something called rational. It's grid over rational numbers, and you work in a new field L of I, where L is a carefully engineered high-degree real number field. So I'm not going to say much about the detail, but the model basically spells out its intuition in its chain of thought. It says that the degree and height of the algebraic relation can be enormous, but that actually can be a good thing. So that model carefully chose this number field so that it actually works, this construction. Okay, so after we got we discovered this solution, we try to see like how success probability of the model correlate with the test time compute we spend on the problem. So as you can see, if you put more and more test time compute, you have higher and higher success rate on the problem. So thinking longer definitely makes it more likely to find a correct solution. And in a sense, the model, if you look at COT, the model can introspect and realize it's not making progress in one direction, or it's making some mistake, so it can self-correct and just keep going. So. So from there, like I think it's good to like review or like introspect on how much progress AI has made. Like how do people what's the best way to measure maybe AI progress? So Meter has this fantastic graph plot on like the x-axis is the years, and the y-axis is for some task, what's the amount of human time you will have to do it. And so the plot is on like at this time like what's the human time of task the agent can reliably done for us. As you can see, this is basically it's basically doubling every 6 months. Like the length of human work that can be done reliably by AI is kind of doubling every 6 months. Of course, this Meter graph is mostly in the area of coding. Yeah. So let's maybe take a look on AI as well. So like almost 2 years ago, the model can solve any problem. Like that's you can think about that as maybe 20 minutes human time for a very good high school students, right? Like Amy is it's not very hard. Then let's say a month later, a year later, AI can solve IMO problems. Those problems are way more harder. They are like maybe 90 minutes of human time for top high school students, right? So then another year has passed, so AI can solve long-standing open problem in discrete geometry. So how many hours does that cost to human? So if we put things on a scale, I would claim that, so in a sense, this is roughly like 6 hours of top human time, but assuming them actually knows all of mathematics. The reason is that this proof is not that deep in the sense that it requires you to understand some ideas from a very distinct field and apply them back to discrete geometry. Like you have to be a very good algebraic number theorist and a very good discrete geometry to do the proof. But if you are very good in both of them, then it probably only takes you a day or two to really push to the conclusion. The challenge is really to master two distinct areas. So in that sense, AI has this very unique advantage here. They have very broad familiarity across all mathematical fields. And they are decent in many subfields. Finding this kind of example does not require extreme human time if the human already has the right expertise. But it may if they first must learn the area, because learning the area takes maybe 2 years or so. But if you master of them, then it's different. So in that sense, AI can shorten the search, can do this math do some type of mathematics better than human just because they know a lot of domain knowledge. As they can think longer and develop better domain knowledge, progress on unit distance reflects this multiplied effect on both trends, like thinking longer and better domain knowledge. And so in a sense, some other mathematical results, they require years of work from the mathematician by pushing deeply on one topic. It's unclear whether we are at that point yet with AI. And after the unit distance, the model we released 5.6 so, which is very, very good at mathematical reasoning. There are so many public results already on them has done by 5.6 so in the past 2 weeks. And also, yesterday we just announced 10 more results in mathematics and theoretical computer science on different area. Oh, so I think it's already there. So I want to say a little bit on how do I view the consequence. So I think AI is especially good at connecting distant fields of research, just as how they solve unit distance problem. They connect different fields. So I think mathematicians will be really empowered to use ideas from different fields, which may feel less familiar to them, and because AI can just find the relevant ideas and explain them very well. So indeed, mathematics is never about just problem solving, right? The most important human input to the OpenAI solution to unit distance is actually Paul Erdős, who really posed this beautiful question with a simple statement and a very deep solution. So AI found the solution, and the human understood it. And actually, after the release of OpenAI proof, that at least 5 or 6 follow-up on this result by different groups among in the world. So I think AI will make it much easier to iterate on which deep question I was asking, because you can find a common example very easily. And also finally, like, the ability to do precise calculation used to be a big part of math. Calculator and then computer really empowered you to do more. You don't have to do calculation yourself. So in a sense, with coding models like Codex and Cloud Code, programmers actually spend more time coding because there's much more they can do once they are empowered. I think similarly, like mathematician will also be empowered to use AI to do more math because now you don't have to do tedious calculation and you can just like maybe focus on high-level ideas or like enjoy the process. Okay, that's all. Thanks.
All right, thank you, Lijie. Next up, we have Vijay with Georgia Tech. There we go.
Okay, cool. Thank you. All right, welcome. My name is Vijay Ganesh. I'm a professor in computer science at Georgia Tech, and I broadly work in the area of formal methods and neurosymbolic AI for mathematics, physics, and code. So the problem that I'm focused on is a little bit different from the problems that the previous two speakers talked about. The problem I'm focused on is called auto-formalization. What does that mean? Auto-formalization means you want to translate natural language math into formal language math, okay? So let me define this a bit more precisely. Natural language math is written in languages like English, French, etc. By formal language, I mean languages such as Lean, and I'm sure many of you have heard of Lean, okay? Or some other theorem-proving language. Now, why would you translate natural language math into formal language math? What's wrong with natural language math? The problem is that often human-written proofs are incomplete, meaning they are missing steps and the human mathematicians may not be aware of that. Worse, sometimes the proofs are incorrect. By translating from natural language math to formal language math, we can deploy the Lean theorem prover and we can check whether or not the theorem was indeed proven, right? So now we want to build a box that takes as input natural language math and produces as output equivalent formal language math. What do we mean by equivalent? What we mean by equivalent is what I refer to as semantic equivalence, meaning that the semantic content of the Pythagorean theorem that is input to your box must be the same as the semantic content of the output Lean. It must talk about right-angled triangles and the relationship must be the same, okay? That's what we mean by equivalence. So the task we set ourselves was the following. We wanted to build such a box. We wanted this box to be 1,000x smaller than the frontier models, at least 1,000x smaller, maybe even smaller. And the question we posed was, how do we train such a model? How do we build such a model such that it outperforms the largest frontier models out there on this one task of auto-formalization, okay? So the property that I came up with, I call as semantic alignment. The concept of semantic alignment is not new. People have talked about it in many settings, but in mathematics, it takes a particular meaning. What we mean by semantic alignment with respect to the auto-formalization problem is as follows. So recall again what the auto-formalization problem is. You have natural language math represented in one modality, and formal language math. And what the property that we want the model to possess is as follows. If the same object, if two objects which are represented in different modalities, but they have the same semantic content, then we want them to be close by in the embedding space of the model. If they have different semantic content, then we want them to be far apart. And by imbuing the model with this property, what we then do is we make it much more effective at the auto-formalization problem. At retrieval time, when you do the retrieval, it's far more effective. Now, this is valuable not only for translating natural language math into formal language math, but it's also valuable when you do code translation from one language to another, or if you're going from a specification to a circuit, or if you want to connect definitions from different areas of math, you want to see relationships between different definitions in different areas of math and thus discover new math and be able to do that with very small scale models, not necessarily having access to frontier models. This property can get you there. So we trained our models using this technique, and we developed a particular recipe called semantic contrastive learning, where we imbued the model with this property, meaning that if two objects have the same semantic content, they're close by in the embedding space. And the result was a far more powerful model than frontier models on all the benchmarks that we tested. And now we are taking this idea and to the setting of code translation. So we're building a tool that would take programs in legacy languages like COBOL, translating them into Python, and we are deploying verification tools and automated testing tools on the input program. In this setting, we don't need specifications because the input program is the specification, and we are using techniques like LLM-driven symbolic execution to generate a test suite. Now that we have that test suite, we can use it on the output to check whether or not the input-output programs are semantically equivalent. And of course, this has a strong business case out there for code translation and so on and so forth. So the takeaway is, in settings where you have access to formal objects and you're doing translation of formal objects or even informal objects from one modality to a formal object in another modality, or two formal objects, then imbuing the model with the property of semantic alignment is a great way to build a system that can scale and be at a much smaller level, but still be able to scale to much, very large code bases and so on. With that, I'll end my talk. Thank you for your attention.
All right, thank you, Vijay. That's it for our talks. We have a workshop from Databricks. I think Aravind, if you're here, if you want to step up and lead that workshop.
All right, hello everyone. My name is Arvind. This is Dhruv right here. We both work on Omnigent. It's a Databricks. It's a multi-harness, and we're excited to share all about it. It's going to be a workshop kind of thing where we're going to demo some features of Omnigent. If you guys are curious and want to follow along, you can start downloading it at omnigent.ai and quick start and then install it. It should be pretty simple. If you guys have Claude Code or anything set up on your machines, we'll be starting to use that. But no pressure. You can also just follow along, listen to the demo, and you can also try it out after as well. So yeah, with that, let's get started. What is Omnigent? So, oh, there we go. You guys are all familiar with this screen. This is our lovely Claude Code. Everyone uses it every day in order to do all your tasks, do all your coding. It's an amazing harness. I think they come up with like crazy features that every week. It's impacted our industry a lot. But then Claude Code is not the only harness out there. Building harnesses are easy, and a lot of people have done it. Let's take a show of hands. Who has used Claude Code before? Awesome, awesome. Codex. There we go. Like Kiro. Have you guys tried that? Awesome. We got some nice ones. Pi, anyone? Nice, nice. So yeah, there's a whole bunch of harnesses out there, and everyone's using them. But the problem is, it's very hard to operate them and adopt into them. And we at Databricks saw this firsthand. We have over 3,000 engineers, all using different types of AI tools, and we found that it was very hard to make a unified ecosystem. Adopting agents is pretty easy, but operating them is not. And some problems we saw was, first, this space is very crowded. There are a lot of harnesses with a lot of models, and with that combination, there's like infinite possibilities. There's new ones coming out every week, and it's very hard to keep track of everything that's going on. This space is very fragmented. Each harness locks you into its own code. And switching harnesses means rewriting your custom agents you have, rewriting your skills, rewriting your tools, your policies, or any additional configuration that's specific to a harness. It's also very, very personal. All the agents and your memory lives on your laptop, and no one has access to it. And nobody else can see your sessions, steer your sessions, or even contribute to your sessions. And at an enterprise level, it is very hard to govern these agents. People can have policies set up on their local Claude Code machine, but if you want to have enterprise-level spend caps and have access rules to actually govern the tool use behind your agents, it becomes very hard. And finally, it's tethered. It's connected directly to your laptop, and once your laptop is closed, died, like out of battery, you can no longer work on it. And you are always walking around meeting rooms with like your laptop half open with your finger in the middle to make sure the cloud code is still working. But these are just some problems, and there's a lot more. And that's why we have figured out that we need something to do 3 different things. We need to understand, how do I compose agents with a different harness to do the same task? We need to understand, how do I collaborate with agents across humans and other agents? And finally, how do I control all my agents for the cost and security? And we have faced this firsthand at Databricks. People used to send Claude MD files across like Slack messages to understand, oh, my agent did this. Can you add your agent and ask it to do something else? We would have private work trees set up where we were committing pseudocode so that like we could collaborate together and get some sessions. We would try, as soon as we started wanting to use Codex, we have to reconfigure all our MCP servers to make sure everything is online and like working with our internal systems. And that's when we realized what we need is we need a new layer, a new open layer above the harness level, and that's what we're calling a meta harness. And we have set out to build this meta harness, and we have built Omnigent. It's a meta harness for AI agents. Omnigent is a completely open source project that you can contribute right now. You can try it out. And it gives you an agentic development environment. You can use it on your desktop, mobile, any other platform you want. And it gives you the ability to go through and use any harness under the hood with your existing setup, and enhances your experience a lot. And to go through like some technicals of how Omnigent actually works, Dhruv here is going to walk you through some of our slides. Yeah, I'm just going to hand it over.
All right, thanks, Arvind. So that's the why behind Omnigent. Let me show you what Omnigent really is. The model here is deliberately quite simple. There are 2 halves to it. There's a server. That's where your sessions live. So all your session history, your policies, your MCP servers, skills, they all live in one place. Your custom agents are also stored here. And on the other hand, we have a runner. And this is where the agent is actually doing its work. So this could be your laptop, some sort of dev box, a Kubernetes pod, or some sort of cloud sandbox. And in between all of this, it's one common API, and every surface speaks it. So the terminal, the web UI, the native desktop app, all of them speak the same API. And because of this, because the server sits in the middle of all of this, a session is no longer trapped to one terminal on one machine. So you can close your laptop, and this agent keeps working. You can pick up the sessions back up from your phone. And this one architectural choice buys us a few things. Firstly, we get composition. Every harness plugs into the same layer, so you can combine agents across harnesses and models, or switch harnesses mid-project without rewriting anything. Secondly, you get collaboration. Sessions live on a server, so they're shareable. You can bring a teammate into a live session to watch, steer, or comment on the files and other artifacts that your agents are producing. And like Arvind mentioned, there's no more screenshotting your terminals and sending it in markdown formats. Thirdly, we also get control. So since the server sees the whole session, it sees every prompt, every tool call, every file that has been touched, that makes it possible for us to have genuinely smart policies for both security and cost, as well as a strong OS sandbox. Let me go a little deeper into each one of these. So out of the box, Omnigent can speak with over a dozen harnesses. These include Cloud Code, Codex, and I will not read out the whole list here. And 3 things matter here. First of all, there's no migration needed. Omnigent will pick up the setup that you already have on your machine. So if you already have your subscription setup, your MCP servers, your skills, those will already come along ready to go within Omnigent. Second is this orchestration across your harnesses. If Cloud Code has a capability tomorrow that Codex does not, you don't need to open a second terminal and copy your context into it. You can ask for it from the same session. Have one model implement the code and have another model review it. Thirdly, it's very extensible. We have a harness plugin SDK system, which allows anyone to ship an integration without touching the core Omnigent package. For example, we had folks at Atlassian who built their own custom harness called Rovo, and they integrated it with Omnigent without having to touch Omnigent at all. And because different harnesses are really good at different things, this becomes really powerful. On top of harnesses, you can also define custom agents. So an agent is just a YAML file within Omnigent, which consists of a system prompt, a model, some tools that you might want to give it. And the fun part is you can also start adding other agents as tools. And these other agents can be built on different harnesses. My favorite, we ship a few examples in Omnigent, and my favorite is one called Poly, which we'll actually demo in a little bit. Poly is a multi-agent coding orchestrator, and it can fan out tasks across harnesses in parallel. So you can have Claude Code, Codex, Cursor, and as many other harnesses as you want, implement and review all of your code in parallel. And so because agents are also plain YAML in Omnigent, they're very portable. You can share your agents with your team, or you can publish them across the whole server, and the same policies and sandboxing apply to all the custom agents. Next, we have control. Policies in most tools look at one action in isolation. Is this command allowed or not? Yes or no? In Omnigent, policies see the whole session. They can see the data that has come in, the action that's being requested, all of it together. And the enforcement is very granular, so you can have a policy either allow, deny, or ask for human approval. We ship a library of built-in policies, and policies are just defined in Python, so it's very easy for you to add your own policies. For example, we had a couple of folks at Red Hat who developed policies to identify when their agents were getting stuck in loops and stop those agents. And the same machinery that watches security also watches your cost. There's two main cost built-ins that I want to talk about today. First is budgets. Most of us have some sort of monthly or weekly budget for our AI usage. And in the middle of a session, you don't really have a good idea of how much money have I spent so far? How much money have I burned? So the budget policy gives you soft checkpoints. Say your limit is $100. At $20, it'll prompt you saying, hey, you spent $20. Do you want to keep going? And the part I like here is that this is not a hard limit, or you can configure it to not be a hard limit. You can have it to be a downgrade gate. If I have spent $20 on the frontier models, maybe I start downgrading to more cost-effective, cheaper, smaller open source models. There's also a per session version and a per user daily cap that you can enforce server-wide with policies. Secondly, we also have smart routing. I myself am completely guilty of picking the biggest model at the highest effort level for even the smallest task that I do. And we have a better option in Omnigent now. With auto option, we have a lightweight classifier that looks at the task and picks the harness and the model for you. So if it's a big design task, we can pick a frontier model. If it's a small fix or an easy question, we can pick something that's fast and cheap. Next, we have collaboration. This is a feature that I personally use the most within Omnigent. Any session can be shared, either in a read-only mode or a full edit mode. And someone can co-drive your sessions with you. And again, we'll demo this in just a little bit. So the pattern that we constantly see is very typical to how on-call runs. Someone spends an entire hour building up context with an agent about some problem, and then they hit a blocker where they need to pull in a teammate. And instead of copying in their history or their final Claude response into Slack, you can pull a teammate into the session with you and have them drive your session with all the context already in place. Moreover, you can also comment on all the artifacts that have been produced, so almost like a Google Doc editing style, but for agentic work. So you can comment on code, Markdown, HTML, and PDFs. And once these comments pile up, you can just press the address all button on the UI, and they're injected into a prompt that goes to your agent. So everything I've shown you so far runs wherever you want it to run. On the cloud side, Omnigent connects to a lot of sandbox providers through one interface. So we have support for Modal, Daytona, E2B, plain Kubernetes, and we also have a Databricks sandbox, which runs the agent inside your Databricks workspace. So cloud sandboxes are what give you this always-on story. You can kick off a session from your laptop, you can close the laptop, you can check in from your phone, from anywhere you are, and all these providers are plugins as well. So if you have some sort of DevBox setups that really works for you, you can build a plugin for it in Omnigent and bring that DevBox setups into Omnigent with little ease, with very little difficulty, and no need for PR reviews from any of us. And for defense in depth, we also have Omnibox, which is our built-in OS sandbox. So this contains the agent at an OS level, which is native to Linux, macOS, and Windows. We have credentials that get injected at a proxy, so your agents will never see your real credentials or raw secrets. This also applies within cloud sandboxes. So even when you're using a cloud sandbox like Daytona or Modal, you will already have an OS level sandbox built in, so the blast radius is always small. So that's the idea. AI needs a layer above the harness. The harness ecosystem is going to keep producing great tools every month, and you shouldn't have to commit to one of them. Everything I've shown you so far is open source at omnigent.ai, and rather than keep telling you about this, I'm going to hand it back over to Arvind, who's going to show you the whole thing live.
Awesome. Let's see a demo. Yeah, feel free to follow along if you guys have it installed. But yeah, let's just go ahead. So for this demo, we'll be looking at this one amazing repo that Claude made in 30 minutes. It's called a note-taking app. Is it working? Yeah, it's called a note-taking app. It's a basic note-taking app that we have built, and we have some issues that we have filed. We have some stuff like, hey, let's add a dark mode. We have some stuff to put the important stuff on top. Okay, yeah. So we'll use Omnigent to tackle all these issues today, and I'll show you how Omnigent works. So let's go into our terminal. Let me zoom in. Okay, I'm assuming. Can you guys see that? Awesome. So before you would run something like Claude. Oh, now you would just run something like OmniClaude. So you would just run OmniClaude. And what this does is, as Drew was telling us before, it's going to start a runner, which is our laptop, connect to the server that I've configured Omnigent to be, and it's going to start a Claude terminal. This is the usual Claude terminal that you guys are all familiar with. You can start talking to it, so it'd be like, say hi to the workshop. And this is your normal Omnigent. This is your normal Claude session. Nothing fancy. You can just get started with what's going on. But the one extra feature that we have is we have a URL right here. This is our Omnigent URL. When you click on this, it takes you into our Omnigent UI. I like the desktop app better, so I'm just going to open the desktop app, but you can also use from the web. So if we go into the, oops. I'm going to choose the server that we were on. So this is our server right here. So when you open Omnigent, you're greeted with a simple UI where you can start stuff. Here is your host picker. This is my laptop right now, and this could be, can you guys see this, or should I zoom in more? I think that's probably better. Yeah, so, sorry? How do I increase the font? Oh, I can go into my settings. Appearance, doing this live. Let me zoom out a bit, and then let me just go to like 35. 4. Oh, I guess it maxes at 20. Okay. Yeah, I think that's a little better, but we were maxing at 20. Yeah, so you can use your laptop or any sandbox right here. So my laptop is currently connected. I have some other hosts that I use, but currently it's my laptop. You can choose the folder. So this is currently my laptop's working directory. I've chosen the best note-taking app ever. We can have any work tree that we can configure. And here you can configure your current harness. So I can configure like Claude Code, Open Code, Codex, Cursor, or any of the custom agents that Drew was talking about. So we have two built-in, Polly and Debbie. Polly is our multi-agent harness, which will allow you to orchestrate between multiple agents. And Debbie is like our debating agent, which will basically run the same prompt across multiple different harnesses, and you can compare and contrast what's a better one and choose ideally. And you can also do custom agents. So if you have like custom agents you defined that for a specific task, such as like give me the brief every day, in the morning of all the PRs that have been going on, then you can define a simple YAML spec to do that, and then go ahead and use your custom agent. So now let's go back to the Claude session that I started, and that's going to show up right here on the left. So this is my Claude session where I asked you guys to say hello, and you can interact with the Claude session in 3 different ways. You can interact with it in our chat UI, our web terminal UI, and also your Claude session. So everything is synced. So if I go here and I type in hi, I'm now talking to my Claude session. So you can either interact it with like a web GUI, with your exact terminal, or with a terminal on the actual web UI. And everything is synced, and nothing has changed. And now you're basically using your existing Claude code, but in a much more nicer GUI, allowing you to look at all your sessions, have projects, organize them, making it much better. Now let's go into some of Omnigent's cool features that we talked about. So now if we go back into Omnigent, I'm going to show you our command called Omni Setup. So this is how you set up different harnesses. In my current demo, I've set up 4 harnesses for us. I've set up Claude, Codex, Cursor, and also OpenCode. We support a dozen different harnesses that you can set up, and it's very easy to set up if it's already set up on your local computer. So remember the GitHub issues I talked about? So let's start working on those. So what I can do here is I can then go into Poly, and then I can choose, I'm using Claude SDK as my main agentic harness in Poly, and I'm going to tell it to look at all my GitHub issues, and then use Claude, Codex, OpenCode, and Cursor subagents to solve all of them. And let's send it away. So that's all you do. Poly is now going to look at our GitHub issues. It knows exactly how to start all these sessions. It will monitor them for you, and it will make sure that everything is working. So while Poly is working, let's look at some other stuff. We'll come back to this as it takes a little bit of time. So this is another issue that I was looking at. This one, for example, was telling me how I should do dark mode. My agent has done some stuff, has done some files, and we have an embedded browser, so you can easily go into the browser. I think my agent said it's at localhost, so I'm just going to go to localhost. Yeah, so that's my best note-taking app ever. It has done some stuff here where it goes in and then says, oh, that's my dark mode and light mode. And with our embedded browser, you can also comment on it. So for example, I can take the tooltip and I can just be like, you know what, I don't like this. Let's change this to a toggle. And that's it. Our agent's now going to work. It knows exactly what we need to change, and it's going to work on it. And the other thing is, now I'm ready for some reviews. Let's see what happens. My friend Dhruv here made this app, and I want his opinion on it. So let's show sharing. So I can share my session with Dhruv. And I can give him edit access and also approve access, so he can actually go ahead and modify my session and look at my code if necessary. I'm just going to grant him this session. And now let's switch, and hopefully the demo gods are with us while I switch my laptop.
All right, this is my Omnigent, and I can come in here onto the UI, and I can click on the Shared With Me tab, and let's see if Arvind's session pops up here. It is, so here it is. Arvind, is this the right session you shared with me?
Yeah.
This is, okay.
Yeah, you can see me on the session right there as well.
Oh, I see you're online, cool. All right, so now I can go into, which all files have been changed. Let's say I want to go into this file, and I'm just going to start adding some arbitrary comments here, like this code is slop. Please fix. I can add this comment. Arvind can also start adding comments here as well. And once we're all done, I can click address all. And this will send a message on my behalf to Arvind's agent, which is running live on his laptop. We can switch back to Arvind's session.
Awesome. And just like that, I have Dhruv's comment right here on my own laptop. We're addressing some comments. There is no sending it across GitHub. There's no Slack messages involved. He's directly in my session. He can ask questions about how I implemented this specific feature, and we have comments and everything ready to go. So that's one cool feature about Omnigent. And then next, I would like to show you guys smart routing. This is basically Poly again. And here, instead of now saying Claude SDK, we will start saying auto. So this is our lightweight classifier, which is going to use the best model and best harness for you for a specific task. So if I start with a simple question, such as what is the capital of France, for example? This is a very simple task. It should not take a super big agent or a super big model in order to answer this specific question. So let's see what Poly whips up. Nope. Well, I guess a little bit of a weird bug, but it has said that this is a simple task, and it chose GPT-5 Nano in order to do this task. So it's very simple. So it chose the right small size model for you, which is very light and very fast in order to do a simple task. Now, if we go into a more advanced task, for example, like explain this complete code base and give me a diagram of how everything works. So now this is a much more complicated task which requires a lot of coding knowledge. The model needs to be a little bit more heavy duty. It needs to walk through our entire code. It probably needs to give us a more interesting ask. And it says that this is a complex task, and it has chosen Opus for this model. So this is our intelligent routing, and this is also a pluggable starting soon. So if you have your own smart routing providers or gateway providers that you want to integrate in, it's completely pluggable and open source. So you could just integrate your smart routing policies, and you would start using it. And then for the next feature, I'd like to show policies. So let's start with a simple Claude Code agent. And then I'll make it a default Claude Code. And I'll start asking it stuff like, explain this repo. So it's going to go ahead and get fired up. And while it's starting, I realized maybe I should not spend too much money on this. So I'll add a policy. Oops. Yeah. So you can add different types of policies. You can add stuff like, let's limit the tool calls per session. Let's block specific skills. Let's enforce a sandbox. Let's deny PII. For this one, let me add a budget policy, so it's easy for us to control it. So I'm going to set a session cost budget. I'm going to set 10 cents. Hopefully that will hit pretty soon. So it's not gonna, it's gonna easily hit it. And I'm just gonna click add. And now our policy is added. Let's see that it gets picked up. It should. I guess I added it a little too late. Let me ask it a follow-up question.
I think we'll do questions after.
There we go. So the previous one was already a little too late. So now it says the policy came in, it's denied by the policy, it's now set a limit, and it's now hit the budget. And this is something that can be either session level that I've just set, or this could also be server level. So you could define server level policies, so saying every session needs to be this specific budget, or you could just do it for a specific session. We can do either or. Now, let's go back to our poly session where we clicked off a couple of subagents, and let's see if it made any progress. So I think it's this one. Awesome, look at that. Poly has now successfully orchestrated between 5 different subagents. We got Codex, we got Claude, we got Cursor, we got OpenCode. So if we can, and it's the main thing is Claude SDK, which is driving all the 5 harnesses. It's checking up on them, it's making sure they're all doing its work, and it's orchestrating it perfectly. So if we go through each of them, this is Codex. It's working on the edit notes PR, and you can look at the terminal. Now this is your Codex terminal. It's doing its thing. We have the Claude Code running, and then this is the Claude Code terminal. This is all on my laptop right now, and Poly is orchestrating everything perfectly. We have Cursor right here going as well. It's working on some live search issue. You can look at the Cursor UI. You can talk to the Cursor terminal. We also have OpenCode, which is running something about colors. Let's see what OpenCode is using. Oh, it's using Kimi. So it's using Kimi in open source with OpenRouter on her OpenCode harness. So that's 4 different harnesses that you're using all at once. And this is just one example how you can use multiple harnesses to do your work. And it just grows from here. You could get one of the harnesses to code your work and one of the harnesses to review your work. You could use a simple lightweight harness that's fast for small agents and small tasks, and a big heavy agent with a heavy harness for complex tasks. So those are just some of the features. I'll go through 3 more features, and then we'll go back to the thing. Another cool thing is basically our automations panel. This allows you to run scheduled tasks on Omnigent on any of your hosts or any of your sandboxes as well. It's pretty simple. You come up, you just give us a prompt, you give us a frequency of when you want to run this. You say either the host that's online at that time, or you can just pick a specific host, and you can go ahead and run this. This has been very useful for us. Some of the stuff we've done is a PR sweep where we go and review all the PRs every morning and add some comments, a news digest of what happened in the company every morning or every week so that we understand what's going on. So yeah, automations have been super, super helpful for us. And then I'll go into, what am I missing? What am I missing? Smart policies, sharing. Okay, I guess I'll do one last thing, which is our sandboxes. For sandboxes, I'll use a different server because they're not configured here. They're configured on our Databricks server, so I'm just going to quickly switch over. Oh, I guess it's not here. And this here is Databricks Sandbox. So this is a very simple, lightweight sandbox that we have configured at Databricks. Sorry? Oh. And here it takes a GitHub repository, so we can pass it like a, where was it? This is a GitHub repository for Databricks apps that I've configured for this workspace, so I can just pass it in. It's configured with GitHub credentials, and I can go ahead and just say like, explain this repo. And then now, one cool thing is this is completely on the sandbox. So this is not on my laptop. We're provisioning a host, we're provisioning a sandbox, and we go ahead and work with it. So now I can close my laptop, go on my phone, and start chatting with this exact same agent. Yeah. I think that covers most of it. Those are our cool features. We really hope that you guys try it out, but I'll pass it back to Drew for our final couple slides.
Yeah, so I just want to talk a little bit about how the community response has been so far. Here are a few messages that we've gotten on our channels, on both our community Discord as well as our internal Slack channel within Databricks. And it's really been changing the way that a lot of people internally and externally have been working. We've had people in the community starting to use Omnigent in ways that we had not even thought of, and entire teams that are now sharing sessions with each other in order to get feedback from the whole team. And these aren't just a few nice messages. The numbers are also backing this up. So this is about week 7 since we've open sourced the project. We're at about 8,000 stars. 3,000 PRs have been merged since opening. And we have over 360 members of the community who have merged a PR in this repo. And this is just the beginning. And this is the part that we care a lot about, is that we are completely open source. And this isn't just like a marketing checkpoint where we're just open source just to say that we are. All of our roadmap discussions, PR reviews, design docs are all available on GitHub openly. And if you have a big idea, a big PR, something that you want to get merged into this code base, we are very happy to work with you on our Discord, hop on a call with you, and figure out how we can get this merged in. We have dozens of community PRs that get merged every single day without any process except for just our PR review process. And our Discord is at discord.gg/omnigent, and the QR code will take you to our website. Yeah, thank you so much. And I think now we're going to start a Q&A session. So if you have any questions, there's a microphone right in the middle of the auditorium here. Feel free to either walk up or Jules can help pass the mic around. Also, if you had a chance to try Omnigent, feel free to tell us, what worked, what didn't work. We'll also be at our booth after this if you have any more questions.
Hello. Was wondering the policies. Is there a way to have it enforced, like for the company, so that it basically gets rid of the issue of people doing stuff without you knowing it?
Yeah, absolutely. So we support server-wide policies that an admin can configure. So when you're setting up your server for your company or for your team, you can enforce server-wide policies that get applied to every single user and every single session. Sorry? Yes. If you are using the same server, those policies will get enforced on any host that you use.
Hey, thank you. I really like the tool. I checked it out. I'm wondering how y'all are approaching self-improvement for this tool, and especially when it comes to optimizing the harnesses, right? Because there's certain configurations with each harness, which may or may not work for certain developer workflows and work. And I'm wondering how y'all are gonna do that, because I'm interested in that kind of work as well.
Yeah. So the way that we're approaching harness improvements and extensibility, we're trying to learn a lot from Pi. We believe that they did it in a really beautiful way. We're trying to make it so that Omnigent is very extensible. So everything that we're doing with our harnesses, our sandboxes, our smart routing, it should be very easy for you to come in with your own plugins and build on top of Omnigent. I wouldn't claim that we're quite at the Pi level of extensibility just yet, but that is sort of the gold star that we're striving towards.
Gotcha. Thank you. Hi, that was a great demo, by the way. I have a couple questions. First, what's the scale of adoption at Databricks? What's the order of magnitude when it comes to number of agents or sessions?
Yeah, everyone at Databricks is using it. So we currently have over 3,000 engineers at Databricks that we're going to roll out widely too. Everyone uses it every day. In terms of numbers, I think we're at like thousands of sessions per day. It's actually pretty crazy because like as soon as it goes down, sometimes people are pinging us faster than PagerDuty is pinging us. It's like 2 minutes in, there's just like my Omnigen's down, so everyone's like super sticky onto it.
That's super cool.
Yeah.
Also, like architecturally, so do you run these harnesses in a sandbox, like on these cloud sandboxes? And what do you think about the brains-hand separation architecture that like cloud agents were talking about, like in their blog post? I'm not sure if you have heard of it. Like, so I think some companies run their like LLM loop in like a server and run all of the terminal commands in a separate sandbox. But I'm assuming you're running the harness in the same sandbox where the commands are being executed as well.
Yeah. So like it's like we run the agents on the same sandbox or like same host, but we have the Omnibox, which basically surrounds the agent with like OS level protections, so it's not doing anything that it's not supposed to. And we also have like basically our server, when you have any policies or anything implemented, it's like a tool hook on every single harness. So sometimes before the harness runs, we run your policies to make sure that it's abiding to the policies that's been set on the session before you run the actual harness. But the actual harness is like running on your laptop. We're not doing like harness level optimizations just yet.
Okay, makes sense. Thank you.
No worries.
Yeah, a great talk. My question is, when you showed the example of Codex and Claude running in the background, maybe you go over the weekend, you do something else, come back on Monday. I mean, what happens to the context? I mean, it should eventually go down to zero. Does it clear automatically? Does it compact automatically? How you're dealing with this?
Yeah, sure, go for it.
So the way we're doing compaction is just natively on each harness. So, you know, a Claude session will compact with Claude's compaction algorithm. A Codex session will use Codex's compaction algorithm. So when we showed you the demo with the multiple harnesses, our top level harness that we had selected was still Claude. So Claude was orchestrating the other 5 harnesses in our case, which means that our top level agent will also be compacting using Claude's compaction.
Okay, so you said you use Claude to orchestrate the compaction. That's what you said.
In this example, yeah.
This example. Do you have settings? Are you able to set that? Or it's just Claude is deciding when is the right time to compact?
Yeah, so in this example, right, I believe the way Claude is compacting is just, you know, when it hits some threshold of percentage, they auto-compact. And because in our demo, we used Poly, which is Poly is based on Claude, it'll compact in that same logic. But you can switch out the main harness of Poly to be Codex, which I believe compacts a lot more frequently than Claude.
Okay, I mean, and one last question. I mean, there's still an issue upon compacting. I mean, if you keep compacting, like, I mean, even like 3-4 times, you can start getting rot in your context. Right. You start getting garbage. I mean, are you guys always compacting, or do you clear context where you start again from resume MDO? Like,
the thing is, we let the harnesses do that themselves. So, you know, you can use all the harnesses as you normally would, clear sessions as you normally would, and the Omnigen just sits on top of all of that. So we don't really have, you know, our own compaction, our own clearing logic, because we let the underlying harnesses do it how they normally would.
Yeah. And also, our server stores conversations. So if your agent dies and you want to restart it, we rehydrate it from our database where we hold all the conversations. So when you said like you come back 2 days later and you restart a session, we'll hydrate whatever Claude session right there with all the information that's already been sent, and then we'll go for it. But the compaction itself happens at the harness level.
I mean, I don't want to take too much, but I mean,
okay.
There's like one quick risk, which is there's code being developed and being written. Whether you compact 1 million times or like a few times, you might not be able to tell if the code that was produced has some issues. Maybe we can like talk on the side, but
sure,
basically
sure.
That's what's worrying me, is like how you make sure that this will not happen and it's not really controlled by a harness. Mm-hmm. So you need to have lots of confidence with that harness. That's the main question.
Okay, we can talk after.
Okay.
We can talk on the side. Yeah.
Great talk, first of all. So I had a question about the data boundaries, basically data privacy boundaries. So if I understood it correctly, when I set it up on my local, the harnesses are going to be on my local. So, but the common models are like in many enterprise settings, open weight models are generally not basically used, right? we are using the OpenAI models than the Claude models. So in this case, what you are saying, if I understand it correctly, is that the harness is local, but then there is a common server side which multiple team members are collaborating on and using, and the model calls are being made from that server side. Is that correct?
No. The model calls, everything is happening on your local laptop. Like when Dhruv sent that message, it's still running Claude on my specific laptop. You can think of a server as like a thing that just talks, that orchestrates different hosts together. The actual inference and everything is happening on your laptop. So when I showed you the Omni setup, that's when I'm configuring the credentials. So the server does not make any LLM calls. So it's all your laptop.
But when Dhruv drops a comment on Arvind's basically work, is this because you both are on the same network, or like how is
That's where the server comes into play. The server knows how to talk to my laptop. So both laptops send the message to the server talks to our laptop.
But I wanted to understand what infrastructure is that server set up on. Is it on like my proprietary infrastructure, or is it some open source?
It depends on how you want to set it up. So it could be any like multi-tenant architecture, and we just open a WebSocket connection from the laptop to the server, and the server knows exactly which like pod it is in and which pod to talk to the laptop. So any request that comes into that pod will like dial your laptop. Basically.
And one smaller question to this, which I'm almost sure the answer will be what I'm thinking, but you have these policies which you said, right? So if I want to restrict to certain models, I can use any harness, but the policy can restrict that. Even if it is the harness for, let's say, Kimi models, it still has to go to like an OpenAI model, or it still has to go to only Claude model. I can set it up that way, right?
Yep.
Yeah, okay. Thank you so much.
My question is, I've seen your Poly agent. That's super cool. And I would like to create my own agent. And how do I do that on Omni agent? And maybe my agent is a little bit more complicated. It's more than one. I will say this agent call the other one. I have some deterministic logic in it. How do I do this?
Yeah, so custom agents are defined in YAML, like I showed in the slide earlier. I can just go back to that slide. So this YAML file is basically what Poly looks like as well. And you can do the same thing with any custom agent of your own. And if you want, some deterministic workflows around it, you can build in tools like you would with any other agent and use those for your deterministic workflows. Also, we have, sorry, not to cut you off, we have a REST API for Omnigent. So you can use our REST API within your deterministic workflows as well.
Can you speak of like how is this YAML file getting converted to like actual harness that's being run on Cloud Code and Codex runners in the back end?
I will save that for discussion at our booth.
Thank you.
Then you can also check out our code. It's completely open source, so it's all, yeah.